Hi, it's Ethan, back at it again with another dynamics video, and today I'm going to talk about the method of rotating frames. So I'm going to start with an example to help understand this. You have a fixed frame here. This is your I hat, J hat. You have an origin. It's labeled the fixed frame. But now the problem's a little more complicated. See, as you can tell, we're using a method of rotating frames. I know the end's hard to see because of the light, but that's okay. So we'll have a frisbee that's flying somewhere to some other fellow colleague you're playing frisbee with, and somehow there's an ant on the frisbee that can also move. So here's your frisbee. Alright, it's not a perfect looking frisbee, but it will get the job done. So now we're going to use a body frame that is attached to this frisbee. Alright, so you have a B1 hat, you'll have a B2 hat. We're going to call this the B frame for body. This point here will be your O prime. And another thing I forgot to mention, coordinates in this direction will be x, coordinates in this direction will be y, of course, and coordinates in this direction, since this is new, this is going to be q1, coordinates in this direction are going to be q2. One more thing, this has to be relative to something to have it mean anything really. And it's relative to the I hat from the fixed frame, which is an inertial frame. So this angle right here, that's theta. So yeah, it's a little more complicated. Right here, you have your point P, where P is an ant that can walk around on this frisbee. It's flying, and yeah. So another thing, just to clarify, the K hat is this way. Interesting way to make a K. Anyways, so yeah, K hat is that way. For both, these are both right-handed coordinate systems. So yeah, I will now start getting into the kinematics of the problem. So kinematics. All right. So start with, a good place to start is the R of P with respect to O. So R of P with respect to O equals X I hat plus Y J hat from this frame, plus, so these are the distances from X, or from O to O prime. Just to be very specific, these are not the distances from O to P, they're the distances from O to O prime. Alright? So from the B frame, you have plus plus Q1 B1 hat plus Q2 B2 hat. So that is your relative position to the rotating and translating B frame. So that is your, that's a fully defined position. And next we're going to get into the velocity of that position. So here you have V of P with respect to the fixed frame equals, I and J are not changing, so X dot I hat plus Y dot J hat. And now this is very similar to the previous video where I derived E hat R and E hat theta. So I'm not going to go into that derivation, but I will show what they equal. So B1 hat dot equals theta dot b2 hat, and b2 hat dot equals negative theta dot b1 hat. So if you want to see a derivation, look at the last video. I'm gonna just get right into it. So q1 dot b1 hat plus, use this, q1 theta dot b2 hat. So that's covered these three terms so far. Last term plus q2, oh sorry, it is a minus actually, minus q2 theta dot b1 hat. All right, so now I'm going to show how this becomes the three-term acceleration formula. So it's a little bit complicated, but I'll do my best to explain it. So v of p with respect to the fixed frame, this will give you the velocity of the moving frame O prime relative to O, or the fixed frame. So hopefully that is decently common sense at this point for someone who's taking the class. And so this is just v of O prime with respect to the fixed frame. All right, so that is, yeah, the absolute velocity of O prime. Now we're going to do something a little bit different. So we're going to have a v of p with respect to the b frame. So that is your relative velocity. So it does not include the rotating aspect, but it does include just like the aspect of the ant like walking around, okay? So that comes from this part, and I did forget something. It is right here. There would be a q2 dot b2 hat. So that also comes from that part. Sorry about that. So yeah, that comes from those two parts. So next, I gotta do something with these guys to make them a little bit simpler, I guess. So I'm gonna create a new variable, or not really create, but identify a new variable that's already kind of there. You have omega as a vector, omega is a vector, equals theta dot k hat. So that's k hat over here, you already have theta, it's nothing really that new. So now I'm going to write this in terms of omega instead. So this is also equal to, use your right hand rule, and you have, I believe it is b1 b1 hat cross, omega, omega cross with b1 hat. So omega cross with b1 hat. Sorry, it is a little bit hard to understand this part of the derivation. So that would be in b2 hat, so that's where that comes from. And then you'll have an omega, negative omega cross with, actually the negative will, I believe, go away, because you will have omega cross with b2, which will indeed give you negative b1, so it'll just be omega cross with b2 hat. So that took a little bit to get to that point, but we did it. So now we take these and we write them in terms of these. So we'll have omega cross with b1 hat plus, there is also a q1 here. Actually, I'm going to put it here. Let me just rewrite this. omega cross with 2, so it's going to be Q1, so Q1 B1 hat plus omega cross with Q2 B2 hat. All right, so now you can kind of see that RPO, kind of like what we did before, is just Q1 times B1 plus Q2 times B2 hat. So I'm not sure, this isn't maybe exactly distributive property, but something similar to that, where this becomes just omega cross with RP with respect to O prime. So that gets you the third term of the velocity part. It's a little confusing. There's other ways to derive it. This is my preferred way, but there are other ways in the textbook. So plus omega cross with RP with respect to O prime. This is your 3-term velocity formula, and now we are going to get the magical 5-term acceleration formula. So this is all the proofs, this is not all the proof stuff, but some of the proofs necessary to go from these things that look not super helpful to things that may be much more helpful. So yeah, for sake of being able to continue deriving, I'm going to erase this part. You've seen it. Hopefully you were able to pause the video if you wanted to copy that down. But now I'm going to continue driving, and it's nice to go from here, so I'm going to do that. So here you'll have a acceleration of p with respect to the fixed frame, alright, equals this whole thing, derivative of this whole thing with respect to time. Okay, now I'm going to try not to mess this up. There's a lot of terms, a lot of derivatives, but I'm going to do my best. So let's see what we got here. So we got x double dot I hat plus y double dot j hat. Alright, that's just from these two guys. And now things get harder because the unit vectors are also changing. Or the, unit vectors of the body frame. So now, let's start with this guy. You got Q1 double dot B1 hat plus, look down here, and you got Q1 dot theta dot B2 hat. Alright, so that term's covered. Now let's move on to this guy. You got plus Q1 dot theta dot B2 hat. Okay. Plus, okay, Q1 theta double dot B2 hat. And the last part is minus Q2 theta, or sorry, that is a Q1, my bad, theta dot squared B1 hat. So that is first 4 terms, taking the derivative of them. Now I'm going to go into these next 2 terms. Okay, I'm going to do that down here. I don't think I'd be able to fit it there. So first guy, minus Q2 dot theta dot B1 hat minus Q2 theta double dot B1 hat minus Q2 theta dot squared B2 hat. Yep, so that term's done. and one more term. Okay, so now you have plus q2 double dot b2 hat plus q2 dot, or actually that will end up being a minus q2 dot theta dot b1 hat. Okay, that's a lot of terms. I'm going to now erase this part down here, take a picture, write it down, and I'm going to continue the derivation from this part to the 5-term acceleration part. So, here is your acceleration of p with respect to your fixed frame. Start with what the first two terms mean. This is your acceleration of O prime with respect to your fixed frame. So this is your moving frame translational acceleration. Moving, rotating frame translational acceleration. So this will just be acceleration of O prime with respect to the fixed frame. Alright, one term down, 4 more to go. So the next one you want to look at is, let's see, here's your Q1 double dot, let's find that Q2 double dot over here, and that will give you the acceleration of P with respect to the B frame. So yeah, 2 terms down. Let's see, what do we want to do next? Let's take care of the squared ones next. How about that? Okay, so this, using the same derivation and right-hand rule we used earlier, comes out to be omega crossed with the quantity omega crossed r of p with respect to O prime. Alright. More specifically, in at least my class that I'm taking right now, we're only looking at 2D, so this becomes something a little bit easier in 2D. This is just yeah, okay. I just had to double check. Didn't want to mess it up on you guys. Negative omega dot squared RP O prime, which makes sense because you got your B1 and you got your B2 right there. Okay, sorry about that delay. Okay, so next you have, let's see, quite a bit more terms. Let's deal with all of the ones that have theta double dot. So you got this guy, you got this guy, and that is going to be your angular acceleration. So that is just omega dot cross with RP with respect to O prime. Alright? Could be alpha, it's your choice of notation. And the last 4 terms turn into something that is a little harder to understand just by having a sense of it. It's the Coriolis part. So this part here, this part here, this part here, and this part here become plus 2 omega crossed with V of P with respect to O prime, I believe. Let me double check. Oh, sorry. So, not with respect to O prime. Some people might read it that way, but I think the correct way is with respect to B. So, yeah, that is your 5-term acceleration formula. Okay, it was quite the ride to get there, but we did get there eventually, and honestly, it is easier to just remember this. Do problems and remember this. Deriving it might help you to understand it. I think it helps you to understand it for me, but it is easier to just write this down many times, do a bunch of problems, and you won't even need to remember it because you'll just know it. So now I'm going to go into what all 5 of these terms mean. So right here, you have your frame translation acceleration. I'm gonna write that right here. Frame translational acceleration. All right, here you have your relative acceleration of point P, relative acceleration. Here you have your centripetal acceleration. You got that omega squared, or theta dot squared, which is omega squared. Without the vectorized portion of it. So this is your centripetal acceleration. Centripetal acceleration. Right here, this is your angular acceleration. Angular acceleration. And the last part is a little bit more interesting. It's got a cool word. It's some of you might be familiar with Coriolis acceleration. Okay. So yeah, it is your Coriolis acceleration. Okay, so those are the 5 terms of the 5-term acceleration formula for rotating frames that are also translating. So now I'm going to quickly try and go through when all but one of these terms are 0. I'll try not to make any mistakes. If I do, try and correct it, like the description or something. Okay, so here is your acceleration, the frame acceleration. That is the only one that's non-zero. Or let me write this down. Right here, all but one is non-zero. Just so, I don't know, people who are hard of hearing maybe can still see that. Okay, anyways, so translational acceleration. So it's not rotating at all. The frame is translating. The bug on the frisbee is dead or tired, whichever you prefer. So yeah, so the bug's not moving, frame's not rotating, the frame is just accelerating, and so this would be 0 because it's not rotating. Omega is 0. It's not starting to rotate either. So yeah, that covers this one. Let me underline that. Okay, next one, it's the relative acceleration. So frisbee, someone's holding the frisbee, okay, so it's not spinning, and yeah, the frisbee is not moving at all, and it's not starting to move. They're not throwing it, they're just looking at it, okay? So then you have this bug, and the bug is just, he's moving. He's starting to move. He's not moving yet, but he's starting to move. So that is your acceleration of the bug walking on the frisbee, relative acceleration. Done. Next one, centripetal acceleration. So once again, the frisbee is not translating, it is just rotating. At this point, it's more of a turntable. So you have this frisbee, and it has a omega, so it has a constant rotation, but it is not. So yeah, so the omega dot is 0 because it's constant. The bug is once again not moving. It's not at the origin, but it's also not moving. So this is the only one that will be non-zero. Okay. Next, angular acceleration. So frisbee is not moving yet. Nothing is moving. Bug is not at the origin, and it is just starting to rotate. and that is it. It's not starting to translate, it's just starting to rotate on a turntable. The turntable example is easier for some parts, Frisbee example is easier for other parts. Either way, there's a bug on it, and the bug can move. But in this example, the bug is not moving. Okay, so the last part is the Coriolis acceleration. Hardest one to understand out of all of them. Some people might have intuition, but I feel like most people do not, including myself. So Coriolis acceleration is right when the bug, let's say for the sake of this, that Frisbee is at the O prime is at the same spot as O. So in this, O prime is O equals O prime. It's probably not the correct way to write it, but that's how I'm going to say it. So this is your I hat, this is your J hat, and you have a constant rotation. And the bug is also moving at a constant speed, or it's trying to move at a constant speed across the Frisbee to get to the other side of the Frisbee, all right? So, look, it's coming, and the only point where this is the only one that's non-zero is right at the origin. So right here, this is where this is the only one that's not zero, okay? After it does that, this will start to look more like a teardrop, I guess. It starts moving like that, but for the sake of very zoomed in at the origin, it looks something like that, and that's where the Coriolis acceleration is non-zero. So I think that was a long video, I think. Hopefully you understood it. If you have any questions, ask your TAs. I might look in the comments to help, but we'll see how my schedule is looking. Anyways, hope that helped, and good luck on your test. You're gonna hopefully do great, and yeah. Oh, one other thing that confuses me is, and I've done it for all these videos, is where I put V with respect to the fixed frame and A with respect to the fixed frame, instead of, you're like, wait, why did that change from O to F? And for V, it changes because you can't have velocity with respect to a point. It just, you think about it, it doesn't really make sense. It has to be with respect to a frame. Same for acceleration. So if any of you had that question, hopefully that clears it up. If that wasn't a good enough answer for you, ask your professor. And yep, that is it.